Everybody, it's Mr. Like. I'm back with another episode looking at vectors today. Now, we've been dealing with vectors a lot. We've been saying that if I want to move one direction, we would call that positive. If I want to move the other direction, we would call that negative. I'm sitting here in the Donald A. Schaefer Planetarium, and I know that that direction over there is due north, and that direction over there is due south. So if I move this direction 1 meter, we would say, as a vector, I moved 1 meter due north. Or this direction here, I would move 1 meter due south. But what if I want to go to that corner back there in the room? How do I get there? Today I want to look at 3 different ways to describe a vector. Remember, a vector is any measurement that requires both a magnitude and a direction. We talked about lots of different vectors in physics. We talked about forces being a vector. We talked about displacement being a vector. We talked about velocity, acceleration. All of these things are vectors. So how can we describe something that is not just in the x direction, not just in the y direction, but in 2 directions at the same time? We actually have 3 ways. Let's go over the first one. Cardinal directions. If you've ever heard of cardinal directions before, you've probably heard them from a compass. A compass is set in north, south, east, and west. That's the cardinal directions. So if we are moving 2 meters in the direction that is north, and in this case it's that way, we would say 2 meters due north. Now, this right here is describing a vector. It describes the magnitude and the direction. Those are the 2 things that you need in order to describe a vector. 3 meters due south would be another way to describe a vector. Now, the other thing that we do with vectors is we typically draw them. We draw vectors in terms of arrows. Whenever you draw a vector, you have to have an arrow with an actual head on the arrow. For our purposes, north is typically up here, south, east, and west, just like a compass. So if I was going 2 meters due north, I would draw a vector and label it 2 meters due north. It would look something like that. If I wanted to draw a vector that's 3 meters due east, it might look something like this. Now, note that my 3 meter vector is a little bit longer than my 2 meter vector. If I wanted to do this really precisely, I would actually use a ruler or something and make this one 20 centimeters and this one 30 centimeters, and I could draw these vectors to scale. For our purposes today, though, I'm just going to kind of eyeball it and try to make some of them longer than the other. What about a vector that is in both directions? Right there. Let's call this one 25 meters per second. We know that velocity is also a vector. So the magnitude is 25 meters per second. How would I describe the direction? Well, in this case, we've got north and we've got east, so we would say northeast. So we would say 25 meters per second, northeast. But I got a problem. If I wanted to get to that other point in the room, directly over there, yes, it's in the northeast, but will I get, if I just say 25 meters per second in that direction, will I hit the exact position? Probably not. I'm going to be somewhere over in there. In fact, what if I had something like this? Winds and airplanes a lot of times will say north-northeast, or this northeast, or east by northeast, something like that. Those are different ways that we can start to differentiate these, but we really need to be more precise when we're dealing with numbers. So the way in which we do these is we would say, let's draw this again. Let's draw it maybe in here like this. So here's my vector, 25 meters per second. What if it's 30 degrees up from east? How we would actually say that is 25 meters per second at 30 degrees north of east. North of east means you start at east and you go 30 degrees north of it. That will allow you to draw your vector. And we can make this angle at any angle we want. We could say 30.274 degrees and be as precise as we want in terms of the direction. All the way around the circle. Let's practice one. What if I draw a vector that looks like this? I'm going to call it 10 newtons. Newtons is a force. And I'm going to put an angle in here, 20 degrees. What do you think this would be called? We would call this 10 newtons at 20 degrees east of south. South is here, we went 20 degrees east of it, and it's 10 newtons in magnitude. That's how we would describe that. Okay? Let me draw another vector here. Let's see if you can do it. I got 45 meters per second squared, and this says 23 degrees. What would you say is the actual, how we would describe that vector? Well, we would say 45 meters per second squared at 23 degrees north of west. You started in the west, you went 23 degrees north of it. Now, a couple of caveats for this. If you're going straight north, we call it due north. Straight south is due south, due east, due west. We'll just call that. Also, if you're going 45 degrees east of north, or 45 degrees north of east, it's actually the same thing. We could just call that northeast. So if you ever actually just see northeast, it really means 45 degrees east of north, or 45 degrees north of east, or southwest, southeast, those kinds of things. Okay? Also, typically our degree marks are typically under 45 degrees. So let's say this 23 degrees north of east could also be described as 57 degrees east of north. North, 57 degrees east of, 67 degrees. 67 degrees east of north. Those actually mean the same thing, but typically we talk about the smaller number as being the more correct. This is called cardinal directions. The second way in which we describe vectors is using something called heading. Heading is actually how planes fly. They fly at a heading of 224 or something like that. Heading and cardinal directions are very easy to relate to one another, and we should be able to move back and forth between all three of these ways of describing a vector pretty interchangeably. So let me draw a vector up here and let's see if we can't figure this out. I've got 20 meters per second at 35 degrees. 20 meters per second at 35 degrees north of east. That's one way to say this. We would write 25 meters per second at 35 degrees north of east. That's one way to describe this vector. Now, as a plane flies, here's how it works. North is 0 degrees. East is 90 degrees. This is 180 degrees. This is 270 degrees, all the way back up to 360 degrees. This is the heading that a plane flies. Now, I don't want you to get confused with the unit circle. The unit circle starts here at 0 and goes the other way. No. This is heading. This is how planes fly. So another way to write this would be 25 meters per second at 55 degrees. At 55 degrees. Basically, 55 degrees is from the 0 mark. Okay? So, if I wrote 25 meters per second at 35 degrees north of east, or if I wrote 25 meters per second at 55 degrees, it's the exact same vector. You would draw the exact same thing. You would start here, draw it 20 meters per second, that whatever scale you're on, and you would draw it either 55 degrees from there or 35 degrees up from there. Let's try another one. Okay, here's a vector in cardinal directions. I've got 120 meters per second at 22 degrees south of west. What I'm going to do is I'm going to put this in heading. So to put this in heading, I'm going to start with west, which is right here. I'm going to go 22 degrees south of it and draw my vector. This is actually 120 meters per second squared. This is an acceleration. So in terms of heading, what is this? Well, if I look at heading, this is 270. So I'm 22 degrees shy of 270. This is 180, and that's 270. So 22 degrees shy of 270 would mean it would, another way to write this would be 120 meters per second squared at 248 degrees. Okay? These two vectors mean the exact same thing. If I gave them to you in any spot, or any way, any form, you should be able to convert to the other. Let's do a little bit of practice to see if we get this down. Okay, I have three vectors here. And what I want you to do is I want you to change them to the other form. So if it is in cardinal directions, like the second one here, turn it into heading. And if it's in heading, like the first two, turn it into cardinal directions. Go ahead and pause this video so you can see what these are, and then see if you can't work that out. Okay, so this is what I got. For 30 degrees at 70, or 30 newtons at 70 degrees, it actually turns out 30 newtons at 20 degrees north of east. 70 degrees would be 20 degrees shy of 90, which is 20 degrees north of east. 22 meters per second at 18 degrees west of south. That's going to be south. You're going to go west of it, 18 degrees. So that's 22 meters at 198 degrees. Finally, 1700 meters per second at 300 degrees is going to actually be 30 degrees above 270. So 30 degrees above west. So 1700 meters per second at 30 degrees north of west. Your worksheet's going to have some examples of this to have you practice this a little bit more, but this is probably the easier part of today. Let's look at the third way. How can we take all of these vectors and change them into the third way to describe vectors, which is called components? All right, we're going to work with this vector here first. So we have got 30 newtons at 70 degrees. That's what we started with. We also changed that to say 30 newtons at 20 degrees north of east. Those are congruent. Those are the exact same thing, same way to describe the vector. If I were to draw this, it would look something like this. There's east. I'm 20 degrees north of east, and this is 30 newtons. This is actually how it is drawn. So what I'm going to do is I'm actually going to convert this into components. What I mean when I say components is I mean we're going to look at an x component and a y component. I don't like to draw x or y on here because those actually mean displacements, and this one happens to be a force. So we're going to look at the force in the x direction and the force in the y direction. Now, later on we're going to figure out, which we probably already know, that these can be looked at independent from one another. So how do I get this component down here? We'll call it f of x, and we'll call it f of y. That actually, I like that a little better since this is a force. Well, f of x, we're going to have to do some trig, right? So I'm going to need some trig music for this. Hit it. Okay, so I got 28.2 newtons down here and 10.26 newtons up here. So all I did was I took the sine of 20 is equal to the f of x over 30, or the sine of 20 times 30. Or the cosine of 20 is equal to f of y. Actually, this is f of x. The sine is f of y, and this is f of x. Over 30. And so I got 10.26. It makes sense, this is f of x, this is f of y. It makes sense that this is smaller than this since the angle is pretty small. So another way to describe this vector, we can say 30 newtons at 70 degrees, boom. We could say 30 newtons at 20 degrees north of east, boom. Or we could say 28.2 newtons, 10.26 newtons. these three are all equivalent vectors. If I gave you any of those three, you would draw this exact thing. You would draw 28.2 over, 10.6 up. Note that it's very important that you have a head on your arrow. Because if the arrow is actually over here, well, now I'm south of west, not north of east. And this 28.2 would be negative. And this 10.26 would be negative. So the negatives and the positives still denote the direction that we're going. We're going that way or we're going up. So 28.2 at 10 or in 10.26 newtons is another way to describe this vector. We should be able to move between all three of these without any problem. Okay? Now, granted, these two are really easy to do. The trig takes a little bit of doing, but it's no big deal. Throw some trig music on, and you'll be fine. Okay? Have fun. Work through the worksheet. Let me know if you have any questions.